Good morning, everyone. Welcome to this first keynote of SIBGRAPI 2021. Good morning, everyone. And gives me great pleasure to introduce the first speaker of SIBGRAPI 2021. Good morning, everyone. He is Gustavo Nonato. Gives me great pleasure to introduce this first speaker. And I would like to mention that the first time that I met Gustavo was in SIBGRAPI as well, 2002. And since then, we have become friends. Unfortunately, we don't see each other as often as we wanted, but I have great respect for him as a person, as a colleague. He's a very prolific researcher. Professor Gustavo Nonato got his PhD at PUC Rio in 1998, and he's a professor at the Instituto of Ciências Matemáticas da Computação da Universidade de São Paulo, in São Carlos. He's a very prolific researcher, many publications in top venues. He participates also in editorial boards of several journals. And besides his academic activities, he also has established partnerships with companies and government agents. He has a wide range of research interests, for example, visual computing, visual analytics and data science, visualization, and things like that. So I'm really looking forward to his talk. I'm sure it's going to be very interesting. So without further ado, I'd like to pass, at least virtually, the microphone to Gustavo so he can start his presentation. I'm really looking forward to hear it. Okay, Gustavo.
Thanks so much, Vladimir, for this nice introduction. As I told you, it's really a pity that we don't see each other for a long time. And I would like to thank the organizer of SIBGRAPI for inviting me for this talk. It's a big pleasure for me to stay here. And when I received the invitation, I started to think what should be the proper subject to talk in SIBGRAPI. And I start to think about that, and if I should focus in a particular problem, go into very fine detail of a particular problem. And then I, talking a little bit with Afonso, he convinced me to prepare a kind of overview of all my work since the beginning of my career. And I have to say that I had an enjoyable time preparing this talk, revisiting all my work since the late 90s until nowadays, and remember that the kind of mathematical and computational tools I used in that time, the collaborators I had, and so on. So I really appreciate this idea of making an overview of my career. And this visualization here gives an idea how my work evolves over time. So in the very beginning of my career, I worked with geometry processing. And from 2008, a little bit earlier than that, I moved to visualization. And more recently, I started to work with spatio-temporal data analysis with a strong relation with visualization as well. And my main goal is going to be to show the problems I have approached in each one of those three topics, and trying to emphasize a little bit the mathematical and computational tools I have been using to solve the problems. And I will split the presentation exactly in three parts. One part regarding work in my work and my group together with a number of collaborators in geometry processing, then visualization, then spatio-temporal data analysis. So let's start with geometry processing. I will try to follow this kind of chronological order, but split it in these three topics. And this word cloud here shows how which were the topics I used to approach in the very beginning of my career until the first decade of this century, And I played with a number of geometry processing problems involving surface reconstruction, remeshing, and point set surfaces, and so on. And my PhD thesis was focused on surface reconstruction from planar cross sections. That problem was very hot in that time. If you don't remember exactly which what this problem was, essentially the data set was a set of slices of an object, and the goal was to reconstruct the original object from the slices. The question here is that reconstruction from cross-sections is a ill-posed problem, so you don't have a unique solution. You have many different solutions, and the question is, which is the most appropriated solution for the problem I have? So to tackle this issue, we proposed a mechanism that combines graph with a tetrahedral mesh generation and tetrahedral subdivision. So using this combination of ideas, we proposed a formulation where we have one parameter family of solutions where the user can play with this parameter and navigate between the different solutions so that he could choose which the solution is more appropriate to the problem in hand. This slide here shows an example what we can do by moving that parameter. So if you start to play with the parameter, you can connect more or less the branches of the object, and you have a family of those solutions, and then the user can decide which one was the most appropriated one. And this was the first work to introduce this idea of a family of solutions to the problem of reconstruction from planar cross sections. Another topic I worked in the very beginning of my career was the generation of quality meshes directly from images. Most of the works at that time approached this problem in 3 steps. The first step was to segment the objects in the image, then from the segmentation, extract contours, and then generate the mesh from the contours. In our approach, we introduced this idea of combining all those 3 steps in a single one, where the segmentation and the mesh generation was conducted simultaneously. So the idea is combining some image processing techniques, but restricting the operators to certain directions inside the triangles, selecting candidate points to be included in the triangulation, and then we choose among the candidates the one that maximize a certain properties. In particular, we choose to maximize the purity of each triangle. Purity means that the triangle is not crossing different objects in the image. So we keep inserting new vertices until we reach a certain level of purity for the whole triangulation. Once we hit that threshold, then we apply a quality mesh refinement to generate a mesh that is appropriated for numerical simulation, for example. So in this, the main point here is that we are not performing the mesh generation step by step. We are doing everything simultaneously. And we extended this idea to textured images for 3D objects, and also to generate quad meshes using seed points to identify the different type of textures that we had in the image. In the late 90s, the 3D scanners became a reality, and this motivated a lot of work in surface reconstruction from 3D point clouds. And together with a number of collaborators, as you can see here in the papers, we conducted a number of developments in this area. So essentially, the problem of surface reconstruction from point sets was to approximate locally the point set using a surface representation, typically an implicit representation of the surface, and those approximations was performed locally. We proposed a number of different techniques to perform the approximation. We use mathematical formulations derived from the main curvatures, moving least square, partition of unit, and also orthogonal polynomials. That time, the computational power was not as high as today, so the computers were not able to handle large number of data, and since we were generating implicit functions, we had to extract the implicit functions in a very fine level of detail, as you can see here on those images. And to do that, we need a very an adaptive refinement of the domain. So to alleviate the computational burden, we used an algebraic discretization mechanism for the domain, and this algebraic technique helps to save memory and also speed up the computational times. So we could run or process very large point clouds using this discretization scheme, extracting isosurface with a very fine level of detail. We also proposed a discretization of differential operators, in particular the Laplace-Beltrame operator, to make possible to handle the point cloud directly without the need of a mesh. And this idea of approximating the Laplace-Beltrame operator directly from the point cloud allow us to extend editing and simplification mechanism that was originally proposed for our meshed surfaces to operate directly on the point cloud. So we could edit the point clouds, we could apply a simplification mechanism directly from this idea of the discrete Laplace-Beltrame operator. We have also combined point-based surface reconstruction with fluid flow simulation, giving rise to a new front tracking scheme capable of representing the surface of a fluid in a very accurate way and avoiding a number of problems that other techniques presented that time. Another important issue in surface reconstruction from point clouds is to make sure that the object we are obtaining from the reconstruction is, in fact, a good representation of the original object. And the problem is, once you have the point cloud, you don't have the original object anymore. So how can I make sure that the geometric and topological properties of the object I'm obtaining from the reconstruction is in fact correct. And to solve this problem, we proposed a benchmark mechanism where the framework, the benchmark framework, was able to simulate different phenomena that are typically present in 3D scanners. And so we can synthetically simulate the phenomena, introducing certain levels of difficulties to the reconstruction algorithms. And from that, we can then compare and access the robustness of different reconstruction techniques when facing different types of problems or different types of noise that is typically present in 3D scanning data. Remeshing was also an important topic in the early 20s. Together with a number of collaborators, we proposed many different types of remeshing techniques. In particular, we worked a lot on remeshing schemes that convert triangle meshes in quad meshes, or a remeshing mechanism that is able to refine or coarse triangulations adaptively or uniformly. Here is one example of the type of work we did. We built up the Laplace operator, specifically using one of the eigenvectors of this operator to decompose a mesh in different levels of detail, and then applying certain remesh mechanism in each level of detail, we can obtain a refinement of the triangle mesh uniformly or using adaptativity based on curvatures and so on. Here's another very interesting work that I developed together with Luis Velho and Marcelo Siqueira, among others collaborators, where we proposed a local parameterization mechanism that allows to, for example, refine a triangulation in the parametric domain and then mapping the new mesh to the object, preserving a number of properties, as for example, the singularities, the quality of the triangles, and so on. Oops. The idea of converting triangle meshes in quad meshes was really a hot topic, in geometry processing in the first decade of the 20th years. And this problem was approached in many different ways, and our group proposed a new way to convert the triangle meshes in quad meshes using a combination of graph matching to correctly align the quadrilaterals and according to certain templates. So we use the graph matching to define the orientation, and then we apply templates to the triangle mesh to convert it to a quad mesh using some smoothing mechanism to make the approximation respect the curvatures and so on. One important thing about this work is that we have completely control about the singular points. The singularities in quad meshes is kind of undesirable but unavoidable elements, and corresponds to vertices where the degree is different from 4. And keep control of the singularities is very important in this type of problem. In order to have even more rigid control about singularities, we proposed a combination of template-based mapping with topological segmentation, where the object was segmented using topological tools. And the main advantage with this technique, we have guarantees that each segmented piece of the surface is or a torus, a cylinder, or something similar to a disk. No? And that way, it's very easy to map the templates to the top of those two types of objects, and we know exactly where the singularities will be present in the final object. Another interesting idea that we developed in collaboration with Julien Terny and Joe Daniels, Claudio Silva, was how to transfer a quad mesh from one object to another object with similar geometric properties and the same topology. So if you have two different objects, but with the same topology and similar geometry, so how can I transfer a quad mesh from one object to another? And we solved this problem by combining mesh parametrization with near isometric transformations that allow us to make this mapping from one object to the other in such a way that we can preserve the quality of the mesh while distributing the singular points in a very controlled way. You know? So I really like this work because generating quad meshes is kind of complicated problem. So once you generate a mesh for one object, then you can reuse that mesh to other objects with very little effort. Okay, let's switch now to the second topic. Now I will start to talk about the work I have been conducting in the field of visualization. The word cloud here shows an overview of the topics we have been approaching, essentially multidimensional projection, verifiable visualization, layout arrangement, flow visualization, and so on. So one thing that I believe is going to be interesting to highlight in the very beginning is that most of those techniques we have been using to propose new visualization techniques relied on mathematical and computational tools derived from geometry processing. So you can see how those fields, although they are not tightly attached to each other, the mathematical background, and computational tools can be adapted in a very elegant way to solve different families of problems, as I will try to show you in the following. Let's start with multidimensional projection. So this topic has been one of our main research fields since the 2008, 2010. We have developed a lot of different mechanisms to reduce the dimensionality of high-dimensional data, but focused on visualization. So the techniques we developed, the main focus was to map high-dimensional data to a visual space for visualization purposes. That is kind of different from what other techniques like multidimensional scaling and ISOMAP try to do. They try to reduce the dimensionalities in such a way that minimize certain metrics that is not always valid when you reduce to 2D, for example. The distortions might be huge when you do something so drastic as, for example, reducing data from 100 dimensions to 2D. And the main innovation of our work in this field was to introduce the idea of user-driven projections, which allows users to steer the mapping in such a way that you can control where points are going to be projected interactively. And we proposed a number of different techniques to enable users with the interactive mechanism to drive the projections. We rely on Laplace operators, as we did in the context of a geometry processing, also rigid transformation, and radial-based functions. That was a technique widely exploited in implicit surface reconstruction, for example. So we adapt all those ideas to the context of dimensionality reduction. And we explore this idea of user-driven projections in a number of applications. For example, the construction of interactive playlists, constructions of semantic word clouds, image colorization, semantic image gallery, among others. So this idea of interactively manipulate the projection layout introduce a flexibility to the user that is very useful in a large number of applications. Well, there are many different dimensionality reductions techniques proposed in the literature, and those techniques have different properties, and they behave differently depending on the data set, the dimension of the data, and it is very complicated to decide which dimensionality reduction we should use in a particular application. With this problem in mind, we proposed a visual mechanism to combine different types of projections in such a way that the user can identify the combination that produces the least error according to a certain metric. And what is important to emphasize here is, depending on the metric you are using, the behavior of this combination is quite different. So here I'm showing, for example, the three different metrics: stress, neighborhood preservation, and correlation coefficient. And we see that the location where the minimal error take place is quite different depending on the metric. So in that way, the user can play with different metrics and can choose the most appropriate combination for a particular application. More recently, we proposed a dimensionality reduction method that has theoretical guarantees to preserve the zero homology of the data. In other words, the technique preserves the clusters as much as possible during the mapping process. To illustrate the importance of preserving highly connected components or highly connected groups of points in the projection, I'm giving here a comparison between our approach and TSNE. In this picture, we can see that the topo map, that's the name of our methodology, when projecting the data, preserves the highly connected elements. Each colored group of points here correspond to a cluster in the high dimensional space, and you can see that the clusters are well preserved. When we apply TSNE to the same data set, we see that the clusters are spread in the layout. So, and this might lead the users to misleading interpretation of the data, because we know that closely projected points here are close in the high dimensional space, but we don't have any guarantees that points that are projected far apart are not closely connected in the high dimensional space. So the introducing theoretical guarantees to in these projections are very important, and I believe we are one of the pioneers in this direction. In terms of handling high-dimensional data, we also develop a number of techniques that allows users to query high-dimensional data, changing distance metrics, and also interact with data in the high-dimensional space directly. Here I'm illustrating one or two of those applications where we developed radial layouts, in different levels of details. We can run the radial layout in different levels so that you can understand more precisely what is going on in each region of the layout. And also we proposed a methodology to aggregate different disks, one disk for one attribute, so each attribute of the data corresponds to one disk, and then we can interactively play with those disks so that we can align certain properties, and then the layout of the points here align with those properties. So for example, here, this group of points that are here, all those points has those 4 properties, for example. Interacting with high-dimensional space is, until nowadays, a very important problem. And to tackle this problem, we proposed a mechanism that allows users to play with data in the visual space. So we use multidimensional projection to bring the data from the high-dimensional space to a visual space. Then the user can play with the data in the visual space, and then the result of this interaction is mapped back to the original space. And we use this mechanism in a number of applications. For example, for data augmentation, where users can, for example, introduce or define certain groups of points that from which interpolation can be applied, and then from that groups we take back the information to the high-dimensional space, perform interpolations there, and we use this for data augmentation. And as you can see here, the results are pretty interesting. Similarly, we use this interactive mechanism to explore phase spaces, generating different poses from a reduced number of samples, and also to interactively change distance metrics in order to improve image retrieval from large data sets. Vector field visualization was also in our focus. Among the works we did in this area, we proposed some mechanism to embed a vector field in a high-dimensional space, and then use projections to bring the vector field to a visual space on which the user can, for example, color certain regions according to the similarity of the points in the visual space, and then we map back the colors to the vector field, and then we have a soft segmentation of the vector field based on the similarities the user defined in the visual space. A similar idea can be used, for example, to embed the vector field based on topological properties. Using the topology of the vector field, we can embed the data in a high-dimensional space, and then using projection, we can interactively define clusters in the visual space and color the vector field according to these user-defined clusters in the visual space. Optimal layouts is also a very important topic until today. And we proposed a number of techniques to generate optimal layouts, especially from high-dimensional data as well. And in this example here, this idea of optimal layout is essentially to organize information in the visual space in such a way that we can preserve the similarity between the information, avoiding overlaps, and at the same time generating a very compact representation of the data. So in this example I'm showing you here, we are visualizing the result of queries in Google, for example, and showing almost 60 snippets retrieved from Google simultaneously in a semantically organized layout. In order to generate the layout, we proposed a number of optimization mechanisms. In this particular example here, we proposed a mixed integer optimization scheme that takes in account multiple requirements during the optimization. So, for example, we want to make the most important group of elements bigger in the layout. We want to align the layout horizontally to ease the reading of the layout, and keeping everything as tight as possible in order to occupy the least amount of space in the visual space. And this is a kind of complicated optimization problem that we solved using mixed integer optimization. We also developed optimal layouts to visualize genealogical data and document collections. Verifiable visualization. This work, I collaborate in this work with Claudio Silva and Thiago Etienne, among other co-authors here. And this problem was very important at that time, and it is until today. This problem regards the following. Suppose that you generate a visualization for something. How can you make sure that what we are seeing is in fact correct? How can you make sure that your implementation of the visualization technique is not introducing bugs in your implementation has not bugs that introduce some artifacts in the visualization? So this is the problem we approached in this project here. And here is an example of this idea of verifiable visualization for isosurface extraction algorithm. So the idea was to compute the isosurface using a certain algorithm, but at the same time, we have an analytical solution or a benchmark, analytical benchmark to the solution. So we can compare the result of the algorithm against the analytical solution in order to see, or in order to measure how accurate the result is. And what was very interesting in this project, that we applied this verifiable mechanism in a number of well-known isosurface extraction techniques. And for our surprise, most of them had bugs in the implementation. And so here I'm just showing one example here. On the right we see, on the left we see the result of a surface extraction using a certain technique that had a bug. And comparing the result with the expected behavior of this object, we found that the behavior was not correct. Then analyzing the code, we could fix the bug, find and fix the bug, and once the bug was fixed, the algorithm starts to perform exactly as expected. So this project introduced this idea of verification to the visualization community, and we were one of the pioneers to bring this idea in this contest in visualization. You know? We did something similar for topology as well, where we try to access if the topology of the reconstructed object was correct, given a benchmark, and we developed a framework to generate the benchmarks. And once again, we found bugs in a number of implementations, and here's are some examples. No, here, for example, in this simple example, those two reconstructions here on the left was obtained by two different techniques, but the correct was the reconstruction shown in the middle column here. And we see that something was wrong in terms of the implementation, and once we found the bug and correct the algorithm, it started to work correctly. The same idea was used to verify volume rendering techniques, and we also found important bugs in software that are widely used for volume rendering. Okay, let's switch to the final part of my presentation, where I will show quite recent work we have been doing in spatial-temporal data analysis. And one interesting point here is the type of technique we are using are somehow different from what we did for visualization and geometry process. But when we look more carefully, for example, this idea of graph signal processing, this theory is completely derived from the Laplace-Beltrami operator that was extensively used in geometry processing and by our groups for visualization purposes as well. So for this idea of using graph signal processing to understand patterns on spatial-temporal data, we propose a number of different techniques. In particular, we use graph Fourier transform and graph wavelet transform to analyze signals defined on graphs, and we use this graph Fourier and graph wavelet tools to identify unexpected and expected behavior of the data in graphs. In particular, we apply this technique to identify what was expected behavior of taxi pickups in the south part of Manhattan, and we found very interesting phenomena here. If you want to more details about this, just reach me out and we can talk about it. The same mathematical infrastructure was used to analyze dynamical networks in such a way that we could identify seasonal behavior of the network and certain outliers or certain connections and phenomena that were expected and unexpected in a dynamical network. We also proposed a graph version of the well-known Laplacian of Gaussian filtering for edge detection, and we extended this edge detection mechanism to operate on signals defined on graphs, and we used this methodology to analyze crimes in the city of São Paulo. No? And we could, for example, from the nodes detected as edges of the crime signal, we could introduce a notion of entropy, identifying, for example, which are the expected and unexpected behavior of crimes in the city of São Paulo over time. In fact, crime analysis has been a major research topic in my group. We have been developing different techniques to understand crime data and extracting and visualizing crime patterns, and more importantly, to introduce new tools to assist the agents in charge of the public security in their policy making. No? Here's an example of the type of things we are doing. We proposed a new methodology to identify crime hotspots using non-negative matrix factorization. The novelty about this technique is that it can obviously identify as hotspots locations where crimes occurs very often and with large intensity, but also locations where crimes are sparse but significant and should be identified as a hotspot as well. So this new methodology based on non-negative matrix factorization allow us to define hotspot in a new way that was never being proposed before. Another technique we developed to understand crime patterns was based on tensor decomposition. The idea here was to understand the behavior of crime in the surroundings of schools in São Paulo. Essentially what we did was to collect information about crimes, about social economic factors, and some infrastructure information like bus stops, bars, flow of people. So for each school, we defined a radius of 200 meters, collect those informations in these radius, combine those information in a tensor, and using tensor decomposition, we could extract certain patterns for each school. No? So here, for example, I'm showing one of the patterns. For example, here is a school where with a large number of bars, a large number of passerby robbery, and so on. And from those patterns, we can cluster the schools with similar behavior. No? And doing that, we could uncover a very interesting phenomenon. For example, we identified schools located in socioeconomic regions classified as A, B, so are good neighborhoods. And the schools that are located in locations classified as A, B, that has a large number of bus stops, also presents a large number of crimes. So when we see this polygon open in the downside here, we know that the neighborhood of this school presents a lot of crimes, different types of crimes. And more interesting, the schools that has a large number of bus stops and a large number of crimes, the students from those schools have a worse performance when compared to students that also comes from schools belonging or placed in regions classified as AB, but that doesn't have a large number of bus stops and a large number of crimes. So this kind of spatio-temporal data visualization allows us to uncover a number of patterns and at the same time raise hypotheses why these phenomena are happening. Obviously, we cannot say that a causal relation exists between the performance of the students and the bus stops, but certainly there are certain correlation, and what demands a more detailed or a more depth study of this kind of phenomena. We have also introduced this idea of performing crime analysis using the street network rather than using a regular grid. Most of the techniques devoted to crime analysis relies on regular grids to identify patterns, but as you see in this figure here, regular grids has a number of issues that must be tackled in order to provide reliable analysis. And when we use the street map, we have a much more fine-grained location of the phenomena, and this helps a lot to understand what is happening in different places of the city. Just to give you an example here, our tool is able to automatically identify locations where the behavior of crime changed abruptly. So in this example, for example, we have a corner here where no crime was registered, and after a certain moment, this corner became a hotspot. No, and once the system identified that that phenomena, we can, for example, search for images in that locations in order to explain why that phenomenon is happening. In this particular example, we can see that in this corner over here, in this street in particular, was not allowed to park the cars in one of the sides of the street, and after a certain moment, the parking was allowed. And this might be the cause of this increase in the number of car robbery in this location. We have also developed mechanism to clusterize crime time series. In this particular example, what we did was to use autoencoder to embed crime time series in a high-dimensional space in such a way that we can analyze the clusters in order to identify regions of the city that has exactly the same temporal behavior or a very similar temporal behavior in terms of crime. And this was a very important mechanism, especially for the security agencies, to understand why certain phenomena are happening in different locations of the city. You know, so the police knows that certain behaviors shows up simultaneously in different places, and how to identify that. So this kind of technique was proposed to solve this kind of problem. I cannot conclude this talk without thanking all my collaborators. I have a huge list of people without whom I would never been able to develop all this work I just showed you. So many thanks for my collaborators. And I apologize in advance if I forgot one name here, but I try to dig very deeply in the papers in order to not forget anybody. Thanks very much for all of us, all of you. Thank you very much.
Right. Very, very interesting presentation, Gustavo. Thank you. Thanks a lot. Okay, lots of ground cover here. Huh? So we have probably people are going to start to post some questions. Okay. So in the meantime, let me ask you one, initial question here. So in the early stage of your career, you talk about geometric processing and things like that. And you mentioned that one of the hurdles at that time was that the hardware, the computers were not fast enough. Okay, then slowly, we start to get faster computers. We start to have other technologies like 3D scanners and things like that. So I work more in the other areas like rendering, and one of the things that we notice in rendering is that when we didn't have fast machines, we used to think more about the algorithms, try to make them more robust, use more creativity. And for some reason, the time goes by and you have all these facilities, we got a little bit spoiled and we start not think too much about certain things, and the algorithms are not robust enough anymore. So did you note something similar in your area? For example, at that time when you didn't have access to these fast machines, so you think that, or you feel that you use more, or your group or people who work in this area make more use of creativity to solve the problems, or there is no difference at all?
No, I will not say that people use more creativity. I mean, you have to solve the problem. No, Vladimir. So if you don't solve the problem, you cannot run the experiment. So you have to really dig very deeply all the details of the problem, the algorithm. You have to optimize every single thing in order to get the result. Nowadays, with the increase of computational power, the challenges are in another place. So let's use the example, for example, of deep learning. Nowadays, deep learning demands a huge computational infrastructure in order to be effective, but that is raising another type of problems. You know the results are good, but you don't know exactly why. And this brings new challenges that must be faced in order to properly approach the problem. So then this is giving rise to new mathematics. This is giving rise to new techniques to understand the machine learning models and so on. So I really believe that depending on the constraints you have, you move to a direction or to another. But the problems are always very complicated.
Okay. So another question, okay, for the second part, for the visualization part. You talk about something that I found very interesting, the verifiable visualization. So you could detect bugs and things like that. And you mentioned that you compare different techniques from different authors and you start to see problems here and there. So how people in that area look at this? They start to adopt this kind of approach as well, or they say, oops, I don't want to use that, otherwise I'm going to expose the flaws of my algorithms? Was something that you started, or it became widespread? How people received that?
That's a good question. We were the pioneers in proposing that kind of validation or verification techniques, And from those papers, a lot of people started to think about this problem. And nowadays, I know that there are a number of people working in this field. For example, we have in VIS a workshop devoted to this kind of problem nowadays. And people have been developing even new visualization mechanisms to access visualization techniques and so on. So this becomes a very interesting and hot topic in visualization nowadays.
Yeah, it's very interesting because it was something similar in other areas of computer graphics, right? So in the early days, people didn't care too much about real evaluation compared to the real thing, measure data and things like that. And some people start to look more carefully into that. Okay. Another question for the third part. Okay, you talk about this temporal analytics and data and things like that. And one thing that you mentioned that I thought was very interesting and very important, that you are showing the patterns, okay, but you cannot actually state a causal relationship. Okay, that would be a step further. So, which sometimes people are a little bit concerned that these patterns can be misinterpreted by other people. So you can get, for example, wrong interpretations of this and can lead to misuse of this information. So what the community in this area, for example, think about that? Are there studies try to prevent, for example, this misinterpretation of these patterns?
Yeah, crime analysis, Vladimir, is a very sensitive field. I'll give an example. This tool we developed to analyze the hotspot and to automatically detect abrupt changes in the crime behavior in certain neighborhoods. We developed that tool to work as an app for the phone. So suppose that you are visiting São Paulo and you decide to walk from a location to another, and which path should I follow? Regarding security, for example, which is the most secure path to follow? And when we developed the tool, that was our idea, to propose an app where we use crime data together with other information, to bring more safety to the population, and so on. When we presented this tool to the Secretaria de Segurança Pública, they get really scared about that. They told us, look, you should never release a tool like this one, because might be a person with a small commerce in a certain location, and your software will, for example, deviate people from that street. So you bankrupt that guy. So you have to be very careful about this kind of application. And what we are doing nowadays, we kind of gave up to develop tools for the public use, and we are more focused on tools specifically to the security agencies, to the Polícia Militar, and so on. And you are completely right. I mean, and it's very important to keep in mind that what the tool is telling you might not be the truth. You must have a kind of a balance between what you are observing and and why you are observing that. What are the variables you are not taking account, but might be influencing a lot the results you are seeing there. This is a very important problem, and we face this kind of situation every day.
Oh, I can imagine that. Oh, yeah, absolutely. So just to watch your presentation, I started to think, oh my God, that's going to be very interesting. Okay, I'm not seeing, maybe I'm not doing things right, questions from the audience yet. Okay, maybe they are going to take a while. And
there's a question from Daniel here, Vladimir. Daniel Perazzo is asking the future, if the techniques are going to be a mix of deep learning and geometry processing and so on. Daniel, I'm kind of far away from geometry processing nowadays, but I can tell you, listening my colleagues and other people, especially I had a short conversation with Ian LeCun when I was in New York, and Ian LeCun told me that the deep learning is changing completely the way people is doing computer graphics and geometry processing. So if you see the papers from SIGGRAPI, for example, I think more than half of the papers use deep learning to solve very complicated problems that people strived a lot in the past to solve. But the main problem is what I was telling to Vladimir. You know that the model is solving the problem, but why? How generalizable is the solution, and so on. And this is the main problem with deep learning nowadays. You know that it works for that particular black box there with particular data and so on. And how useful this will be for general purpose use and so on, I really have doubts about that.
In fact, Gustavo, I was looking at the wrong thing here. There are lots of questions. Kind of old guy here. I was looking in the wrong place. But anyway, so let's proceed some questions here. There is one, okay, by Joaquim Bento, okay, and he sent his congratulations, okay, and he mentioned that in the graph signal processing part, the one you talk about GLOG, it seemed to me that the graph relates to a Delaunay mesh. Is that correct?
Not exactly. The glog operator can be applied in any type of graph that is undirected. So if you have an undirected graph, then you can use that technique to identify edges given a signal on the top of the graph. So you have to define a signal on the nodes of the graph, and based on the graph structure and the signal, we can identify the edge. Obviously, the Delaunay triangulation is a particular type of graph, so the technique would also work in Delaunay triangulations, no doubt. I don't know if I answered the question properly, but that's what I understood.
Yeah, that's one of the follow-up things that he mentioned here, right? For example, that if you could use, makes sense to use to another mesh and things like that. I think you sort of cover that as well, right?
Mhm.
One thing, Gustavo, I want to ask you, so more general, more high level, right? You have a very, very successful career here, and you really highlight the point that you made several collaborations, and you can clearly see the positive benefits of collaborations. What would be the hurdles in collaborations? So if you want to give advice to people that are starting the field, start their careers, and they are looking for collaborations, what would be the guidelines, the things that you suggest to people when they are trying to form those collaborations?
The most important thing, let me, is to find the right collaborators.
It's like dating, right? It's like dating. Huh?
Yeah, exactly. Yeah, you have to identify people, obviously, that work seriously, follow the same principles as you. And one very important constraint for me is I have to have a good relationship with that person. It's very difficult to collaborate with a person where the relationship is not easy. So combining skills with this friendship is very important to settle a long-term collaboration. And so this is my main advice.
Very good. All right. Yeah, it's not easy. Not easy, you know. These things cannot take time to develop this, right? This friendship and these connections. So, Gustavo, are you seeing other questions here from the audience?
No.
So one thing that I'll suggest the audience is that you can also ask questions through the Discord channel. Okay, that would be, you can contact and reach out to Gustavo to ask more things. And once again, Gustavo, was very, very nice talk, very nice presentation. It's lots of things. I think we could spend hours talking about all these different aspects of your work, you know, and very interesting applications. And I'm not from this area. For me, it was very, very cool to hear about these things. Okay, so okay, we have some more questions here from Victor. Okay, he asks Gustavo, how to balance the loss of accuracy when projecting data to a low-dimensional space?
That's a very important question, Victor. When you project data from a high-dimensional space to a visual space, in particular a two-dimensional space, obviously you will introduce a lot of errors and you distort the information, somehow. And what we are trying to do nowadays, and the first step in that direction was that work I showed where we try to preserve the zero homology of the data, is somehow to introduce some theoretical guarantee to what we are seeing. You must make sure that certain phenomena that you are observing in the projection are really true. And most of the techniques that we use nowadays, although they are very useful, widely spread, they don't bring any type of guarantees. Even studies in terms of which type of distortion each type of technique introduced is not well settled yet. So I mean, you believe that what we are seeing is the truth. The clusters you are observing are the real ones. But in fact, as I showed in that example, they might not be. And I believe that this field of dimensionality reduction will start to follow a new direction now, in such a way that we can really introduce theoretical guarantees to what we are seeing, making the techniques more robust. Your question is really cool because I don't have an answer to it.
Good. One thing I want to mention while we are waiting for other questions, that remind people that we have another technical section in the afternoon and another interesting keynote talk as well. Okay. And in the meantime, Gustavo, one more high-level question here. So you mentioned 3 parts of your career. What's next Are you going to go to a fourth dimension?
I would like to retire, Vladimir.
Come on, you are too young to retire, man. Okay,
I really want to become a teacher. No, just teaching my students. And I'm joking. I'm joking.
What I think is that you mentioned in your bio that you want to establish connection companies and agents. I think you want to get rich, right? And then retire, right?
Yeah, no, I'm joking. I think this, bridging this gap between the academy and the industry, especially in Brazil, is very important nowadays. And I'm pretty sure that most of the companies are already aware about this problem and how important it is to get closer to the academy in order to become competitive. In this moving world like a crazy, things are changing so quickly that it's difficult to keep up with. During all my career, I really noticed a huge change in terms of behavior of the companies, in terms of the relationship with the academy. In the late 90s, early 20s, I mean, companies look at us like something that, they are there, we are here, and the collaboration should be what you can give to me, without any kind of counterpart. And nowadays it's completely different. I don't know if you know, but we have a center here in São Carlos that is called Centro de Ciências Matemáticas Aplicada à Indústria, and this center exists for 7 years or 8 years, I think, 8 years, I think. And we have already developed projects with more than 100 companies.
Wow.
So, yeah, so things are really changing. And this, I believe, will bring a new perspective for the academic career as well. As used to happen in US, I believe Canada is kind of the same. Researchers in general, they must be collaborating with the industry, and in order to not only to support the research itself, but to take back to the society, the investments that are done in the university. Not the university does not pay off. I don't have any concern about that. I mean, obviously, it pays off a lot, but this new perspective for the future, especially here in Brazil, is quite important, and the new researchers must be aware about that and start their career thinking about this kind of collaboration.
Mm-hmm. Okay. Oh, yeah, it's a very interesting perspective. Absolutely. And Gustavo, I don't see other questions here. Okay. Again, I want to remind people that they can ask questions to you through the Discord channel. Okay. So maybe people are thinking about lunch now or something like that. So I want to, if there are no other questions, we can close this section here. And I want to thank you again. Very, very interesting topic, very interesting talk, and I wish that we can meet again in person soon. Okay, maybe next year, we know.
Me too, Vladimir. It will be a big pleasure to receive you here in São Carlos. And thank you and all the organizers for the invitation once again.
Okay, and one thing, if you come to Canada, you can come visit me here as well. Okay, it's not as nice as São Carlos, but you can manage. Okay.
Okay, right. Thank you very much.
Great, thanks to everybody. Okay, well done. See you. Bye bye.